Hello, thank you for attending DevSecOps 2023. It's a real pleasure to be here. And today we have a talk called Oops, there is somebody in my package manager, and this somebody is us. And we'll show you how to get into package managers. And if you're not familiar with the notion of package manager, Tylet simply estimated that 92% of all commercial software are using open source components. So you need a way to manage these components. You need a way to install them, to update them, even to list them, so you are not missing any of them. And this is something that we call package managers. And usually we have specific package managers depending on the current ecosystem. So for PHP, developers are going to have PHP package managers. For Rust, they will have a different one for all the Rust packages. And today we're only going to focus on package managers for developers. So if you know a bit about systems, you will know that, I don't know, on Ubuntu, you may use dpkg or apt to pull system packages, but this is not what we're going to look at today because it works slightly differently. For software packages, it's most of the time things like front-end libraries, backend APIs to interface with payment providers, any kind of just things and features that you may need. And if you're a developer, you have probably already seen one of these logos. There is Python with pip, there is Ruby with Ruby Gems, there is PHP with Bear and Composer. On the JavaScript world, there is Bower for frontend and Yarn and NPM. There is even one for LaTeX called MikTeX. So plenty of package managers for every one of these small ecosystems. And there's another notion that needs to be known, which is something that we call supply chain, and it regroups all the processes, tools, software, which are part of the life of a product. It's not only for software. It could be anything like if you have a physical product, shipping would be part of its supply chain. And as a result, software dependencies, it's only a small link, because if you push the things like really deeply, like even your laptop on which you're developing your software is part of its supply chain. So it's basically anything that touches your software that's part of its supply chain. Pretty famous is KCD drawing on supply chain is this one. So it displays something that's called all modern digital infrastructure, made of small blocks put all together on top of each other. And one of the blocks that's really crucial for this modern infrastructure to work is a small block that's called, and it's written, the project some random person in Nebraska has been Frank Leslie maintaining this 2003. And in our case, this small project is going to be the backend servers behind package managers. And this backend servers are necessary because when you install a package, you install it by name, and you need to have a way to tie this package name, this identifier, for instance, author/package, to its location. So it could be HTTPS to some random server. It could be a GitHub repository that you need to clone. Could be anything, basically anything that the package manager supports. So if you compromise the backend server that makes this association, you're going to be able to change this association between the name and destination. And attackers are going to be able to force you to download completely unintended archives and software dependencies. And it's likely to lead in the execution of arbitrary code, as you will run the code of this dependency at some point in time. So let's do it. For a quick presentation, I'm going to be helped by Paul today. Paul is going to make the second half of the talk. And my name is Thomas, and we're both vulnerability researchers in the Sonar research and development team. We help drive innovation by finding 0 days in popular open source software. And if you don't know Sonar, our mission is to enable developers to write clean code. That means that are free of functional bugs and security vulnerabilities. And you probably know one of our products. We have Sonar Cube doing this analysis on-premise. We have Sonar Cloud doing it in the cloud, and SonarLint doing it in your code editor. And for today, we're going to show you the result of a research on security of package managers and the backend servers for the PHP ecosystem, because that's the one for which we have the most interesting results. And we're going to start by taking over Packagist, which is the main repository behind Composer, the most popular package manager for PHP. And we did it twice, so we're going to show you how we did it. We're then going to present how we did it for Pair, and we're going to try to give a few insight on how to try to reduce the impact of these attacks and try to prevent them in the future. So let's start by looking at Composer and Packagist. Composer is the most popular PHP package manager. It's used by virtually any company running PHP somewhere. Like if you have a PHP application somewhere, you're probably using Composer to fetch, install, and update all its required dependencies. And it's using a central registry. So like we say, doing the association between the name and the location of the packages. And this registry, it's called Packagist. Both projects, Composer and Packagist, they are all open source and written in PHP, and they maintained, and also public instance is maintained by a company called Private Packagist, which is providing private hosting for packages. And to try to give a very rough estimate of Composer market share. So this is very unscientific, don't do it at home, but it's just to give an idea of how popular this is. It's kind of known that PHP is behind 78% of the internet, which is still a lot, even if its popularity kind of decreased for some time. It's now really back. And WordPress alone is 43% of that. And Composer is not required to run it. So we have to remove this 43% of this 78%. And so we also did an estimation of how many PHP projects would use Composer, and we found something like 70%. So we can say that there is a total of maybe 20% of world servers running Composer in a way or another. And this small graph comes from the official packages statistics, and we can see that there are monthly 2 billion packages which are downloaded from Packagist. So it's still a pretty heavy use of these package managers, even if everybody tried to tell you that PHP is dead. That's really not the case. And in the past years, we achieved to compromise packages twice. So this server, this backend server, we did twice. First time in April 2021, and second time in April 2022, a year later. And these two CVEs, these are two very similar vulnerabilities in Composer that we found. So we discovered and responsibly reported this vulnerability to the maintainers of Composer and Packagist. So let's dive into it. First thing, when you get on the packages interface, you're going to see this small page to submit a new package. And it's really simple. There is only one field where you put the URL of your package, and then you run check. It's going to check if this is indeed a Packagist or Composer package with the right format, the right manifest file, and then it's going to try to import it into package registry. Afterward, any developer is going to be able to import this package and use it as any other. And to do this import, like to clone this folder, Packagist is going to harness Composer for most operation. It's going to check if the project contains a file called composer.json, which is manifest, and it's also going to clone this repository, parse the manifest, create it into the database, and add the right metadata files. So next time somebody runs Composer, they will be able to find this package and download the right source. And when we say that the remote repository is cloned, it's done with the logic that's already implemented in Composer. Say, use Composer as a library to not have to implement it again. And for every single supported version control implementation, it could be Mercurial, that could be Git, it could be Subversion. It will check if it's an on-host, because like if the URL points to GitHub, it's always going to use Git because they know it's supported. But for the other one, they may have like similar tricks. And is it matching the expected format? Like, is there something that's missing? Is it missing the .git at the end? Or is it already present? So there is some small logic checks in there. And then it's doing some further verification on the remote end. And to not implement everything in PHP, because it would need you to understand how this protocol work, and it would be like, it's already done. Like binaries that we are all using, they already do it for us. So they simply run git ls remote --ads and the URL that you just provided. Same with Subversion. They run svn info with the URL that you just provided. And same with HA, which is a Mercurial client. And if you look at this line of code, there is something called process executor escape. So it's an escape function. And the role of this escape function is to prevent command injection vulnerabilities. If you're not familiar with command injection vulnerabilities, I'm going to quickly explain it to you, and it's going to be really useful for what's coming next. So in that case, if in the controlled variable, it's pseudocode, don't worry about the syntax. We put this weird sequence, which is $ and parentheses and dates. And in shell script, this sequence of $ and parentheses is gonna execute what's within the parentheses, in that case date, and put as a result as a string in the current script. So in the case, if you execute it, it's gonna first run, so it's gonna take AJ identify and our sequence. So it's gonna see this command substitution sequence and it's gonna execute it first, and then in the resulting string will be used in the final command, and it's gonna run AJ identify Tuesday, August 2nd. It's pretty unsafe because date could have been anything else. It could have been rm-rf start to remove everything from the file system. So to prevent that kind of command injection, you need to use escape functions. And this escape function will surround the data with single quotes. So the shell will see it as a string literal and not as something it should try to evaluate. And in that case, okay, identify and between single quotes, our injection, and it's gonna just run AJ identify and a string, and the date command wouldn't be executed. But what happens if I try to put -- something like an option? Like, can I maybe inject arguments? In that case, the shell is gonna run AJ identify and -- help in that case, and yes, it's gonna pass the argument help to identify. And if you try it on the shell, the single quotes don't matter, because the shell will remove the single quotes and do the call correctly with 3 arguments, AJ, identify, and -- help. And something interesting in that case, so displaying the help is not so helpful as an attacker, but if you start looking through the Mercurial manual, you will see that it's possible to create aliases with the same name as the existing commands, which can override original definition. So that means that there is a way, by passing an extra argument, like something, it's already something we can do in that case, we can change behavior of existing commands. So that's already pretty nice. And they also say that an alias can start with an exclamation point to make it a shell alias. So this thing would allow us to execute shell command instead of the identify. So with a payload like --config equals alias.identify and an exclamation point, we can put basically any shell command. So if we try to import an URL whose format is --config equals alias.identify, it's going to execute arbitrary commands on the package's instance. And as a result, we would be able to change any software dependency that's hosted on the server. So that's something we reported, and it was fixed within hours in April 2021. So let's look at it. So let's start by showing you how we set up this test instance. So this terminal is root on a virtual machine at this IP address that we can ping from Alice, which is the attacker. So when we go on packages.lo, like local, or this IP address, we reach the test instance, not the real one. So now Alice can go to this interface, register as attacker, like you could do as any other developer, and now you can go on the submit section and put the payload we just show you. So this --config equals alias.identify and then a shell command. And in that case, the shell command is going to be netcat, and we're going to pipe all of netcat's input output to bash, which is going to grant Alice a remote shell on this host. So we can use socat to listen for the connection, get back to us, we run check, and now if we type commands like ID, we're going to see that we run with the www data identity. So this is not very interactive, so now Alice can use Python to get an interactive shell in this prompt. This is what's happening, and now, as we see, we have a real shell. And now let's authenticate as Thomas. So this is me, I'm a developer, I'm hosting an awesome package called Stunning Waffle on packages on this test instance. And as we can see, there is only one version of this package, one release on dev main. So if I want to use it as a developer, I would type composer require and the name of my username and then the name of this package, and then it just works, and now I can use it. So it's simply displaying some emojis with a waffle, sparkles, and a cook. And that's great. It's what I intended to have, and that's why my package exists. But now at the same time, Alice with this interactive shell that just add can go and try to modify the association between my name, so it's the name of my package, standing waffle, with the source. In that case, the source is a Git repo. So if we change this JSON file and try to point to somewhere else, the next time somebody will use composer update or composer require, this is the arbitrary destination that will be fetched from. So in that case, Alice can simply take a JSON file that was modified beforehand and replace the one on the server by the one that was crafted. So now it's being replaced. And next time somebody types composer update, we see there is an update. And as a developer, I did not push this update. So something happened differently. And if I run my main.php file again, maybe something else will happen. Now let's look at how they chose to fix it. The only official way to fix such vulnerabilities is to use a -- sequence. And it may look a bit weird, but in the end, it's part of the POSIX specification. And for any POSIX compliant argument parser, it's when you first encounter this -- you have to ignore all the arguments that come next. They should be treated as operands and not as arguments. So if you create a file called --help and you try to ls --help, it's not going to work because --help is going to be treated as an argument. But if you then run ls space --help, it's going to work because of the support of this -- special argument. And the timeline is really, really cool in that case. Like when you report security vulnerabilities, you really wanted to get it fixed. And most of the time when it's like so critical, you can't wait. You're just syncing your mails several times a day just to make sure you did not miss a response. And in that case, we notified security@packages.org at 1 a.m. And at 10 a.m., they released the hotfix on the public instance. That means that nobody could exploit it anymore for real if somebody already knows this vulnerability. And a few days after, they released a patch version, like an official patch for Composer, and so also for packages. And they released the same day an official announcement. And 1 year later, we're like, okay, did we miss something? Is there anything left on packages? So let's try to identify a new vulnerability in packages just for fun. And a good thing is we are already familiar with this code base. Like we already, paid the initial cost of entry of approaching a new target. We already contributed to the patch. We looked for bypasses, which means that we come with the same set of assumptions and biases, but maybe there is still something. So what did we miss? The first thing, we already know that VCS driver, there's wrappers around all the external commands that's being run. So the git command, the version command, mercurial command. And this is where the first vulnerability happened, because they have to invoke third-party external commands, and that's really risky, either because you can introduce command injection or argument injections. So it's still a target of choice for similar bugs. And is there any invocation without -- left? That would mean that maybe they could be vulnerable to argument injections. And when reviewing the code, we noticed a few calls without this -- so at risk of argument injection. And one of them looks really familiar because we tried to send a patch to correct these lines, but in fact it was removed from a form of suggestions. Like they explicitly removed these 2 dashes for the git and for the mercurial invocation. And they say, yeah, remove fix, because it was breaking a feature. And the culprit is a function called getFileContent. So this getFileContent will allow for any wrapper around git, mercurial, subversion, it will allow to read the file content from the repo. So when you clone the repository, you don't need to have the work review. You can clone a bare repository and then call this getFileContent that will call the right version control subcommand to get the file's content. And so you can also get the file contents at different revisions. So it could be on the main branch, or it could be some old historical branch, or it could be a dark branch. And when you run git show with the end of option, so with the 2 dashes, it breaks because in this subcommand it has a special meaning that's different from the one of the project specification. And its goal is to separate revision from pass. And if we run git show add :composer.json, we get the content of composer.json, but if we put this dash, which should work per the project specification, there is nothing. It's just not working as intended. So that's why they removed this dash. And the thing is, the argument for a call to this get file content, like when the README is being updated for display on the packages interface, the arguments come from composer.json. So it comes from the manifest. The manifest can have a key called readme to give us different readmes than readme.txt or readme.md. Could be don't readme.md. It also works as long as it's part of the manifest in the readme key. And in the Mercurial driver, this value goes straight away. So it's escaped. So it's safe against command injections, but it's not safe against argument injections. So we have the exact same scenario as in the first vulnerability. We can add extra arguments to Mercurial, so the Mercurial invocation. So to exploit it, we would need to create a project in a remote Mercurial repository. We would need to set a malicious readme key in composer.json. And then we would need to import package on packagist. And we could use this vulnerability to maybe write an arbitrary file, an arbitrary PHP script to var www packagist, so under the web root, and we can maybe try to use it to execute arbitrary PHP code, resulting in the same exploitation and the same impact as the first vulnerability that we presented earlier. So in the composer.json, the readme key would contain something like the usual -- config equal alias. This is the cat command, so we override cat and not identify. We put this exclamation point to say it's a shell command, and then we use, since all these repositories are cloned as bear, we cannot just read payload.sh from the local file system. So we use AJ Mercurial client to read the content of a file called payload.sh. We pipe it to the shell to execute it, and then there is a mandatory suffix to reach the right code path on packages. So it executes our update readme call. So .txt in that case. Let's see what it looks like. The setup is roughly the same, but this time we're going to need to host our repository somewhere. So I choose a source auth because this is one of the only few Mercurial hosting services that's left for free on the internet. And on the right, I have 2 windows. These are root shells on the packages test instance. And I'm trying to show and to see if the file main.php in the web root and tmp pond were created or not. And for now, they still don't exist. So we're going to take the URL, the public URL of this repo, and import it in packagist. And in this repo, we put composer.json with a readme that should remind you something because it's a payload we just presented. And this is going to run payload.sh, which is writing the output of command ID in tmp pond, and the file main.php under the web root. And in main.php is simply a PHP script that will execute any command that we put into cmd parameter. So now let's start to log in, and then let's try to import it. So we have a user account. And now we simply put the public URL of our Mercurial repository. We submit it, and the import will happen as for any other repository. Nothing will go wrong for now. But as soon as we click update, we will reach the code path that was discussed earlier. And when the job succeeds, workers are starting to process all the imports. And as we see on the right, we have the output of the command ID in tmp pond, and we now have something in main.php under the web root. And if we try to go directly on this file and try to execute arbitrary commands like ls, we see that we have the output, and obviously with ID we get the same. And now we could do as in the first demonstration, which is backdoor packages by modifying the JSON files of the metadata. So now we can look at the timeline of this bug. So we first reported it on April 7th at 6 p.m., which is a much better work hour. Then we got an acknowledgement like 1 hour after, so it's like pretty quick. We knew that we would be working on a hotfix like right away. They could deploy hotfix on the official packages instance the day after. So it's also like the most important part, like at least nobody could exploit it on the instance that's used by basically everybody. And a few days after, they assigned CV, did an official announcement to say that they did not identify any trace of exploitation on the public instance, except us. And they also released new composer versions to protect everybody that were trying to use this feature from Composer. And to patch, it was not really easy to elegantly fix it because there is this dash option that we need to inject. So they couldn't put dash before it, otherwise it would break this dash option. So they simply prevented any branch name whose name starts with a dash. It's not perfect, but I mean, at least it's pretty effective. So now Paul is going to guide you through similar vulnerabilities in another software package manager for PHP called Pair.
Okay, then let's look at Pair now. First of all, what is Pair? Pair stands for PHP Extension and Application Repository, and it is the historical package manager of the PHP ecosystem. It was created in 1999, so quite old now, and today it's only moderately active anymore. Since its beginning, it served almost 300 million package downloads, and nowadays there are roughly 50 popular packages. They are still being actively developed and published on Pair, and among them are names like Pair, Console Get Opt, NetSMTP, and Archive tar. First of all, before we look into the vulnerabilities of Pair, or before we start to search for them, we have to think about the attack surface. And one big difference between packages and Pair is that for Pair, administrators have to manually validate all new accounts. So how do we really get an account? Well, we don't. We could try to trick an admin into accepting us, but we want to focus on the technical side and not trick people into something. So we have to start with the pre-authenticated attack surface. This includes all the features that you can use before you even log in. And there are some features of that in Pair. A historical package manager also probably means that it was built with historical best practices in mind that are nowadays considered deprecated. And it also has to support older PHP versions. So with this attack surface in mind, we started and we did this. We do what we always do when we start a new research project. We use our own tool, SonarQube, to scan the code of the target. SonarQube is a static analysis tool, so it will look through the code and find dangerous places. For example, where user input lands in a dangerous function, or where certain functions are used in a bad way, or in general functions that are considered dangerous. And in this case, it gave us an issue about pseudo-random number generators and that there's an unsafe one being used here. You can see it down below. The function is empty_rand, and it is in the reset password function. And this is very interesting already, because this is exactly one of those features that can be used before you log in. If you lose your password, if you forget it, then you might want to reset it. And to do this, you can't log in. So this is already a pre-authenticated attack surface. So we dug a little bit deeper into what happens here. And what a reset password function usually does is it generates a random token, then emails it to the user, so the user can click on a reset link, and then they can set a new password. So this function also does this, and the way it's done is like this. It takes 4 different values, combines them, and then hashes them with MD5, and the result is the random token. But some of the values are easily predictable or known by the attacker. So the first part is a random number. This is the pseudorandom number generator function that was raised here. And the two arguments don't mean the length of the number, they are the interval. So this function will only generate 9 different values between 4 and 13, which is not a lot and easily guessable. The second part is the username of the account that has the password that should be reset. So this is also from the request attacker controlled. The third part is the server's local time at the moment of the request. And this might not be so easily predictable, but the server always sends back a date header in its HTTP response that contains the local time. And the last thing is the new password that you want to set. So for pair, the password reset works like this. During the reset, you already give your new password. And once you get the link, you basically accept that this is a new password. So as I said, the last 3 things are either directly controlled or can be known by the attacker. And only the first value is really the one that's random. But as I said, it can only have values between 4 and 13. So it's also very easily guessable. And with that, we can reset about any account's password on pair. So to sum up where we stand right now, we can take over any account with about 50 tries. Sometimes we have to guess a little bit more if the timestamp is a few seconds off, or maybe the time zone, we don't know it and have to try it out, but 50 tries should be enough for any account. And it's also very interesting because pair accounts are public. For a specific package, you know which user published it, and you only need their user account and not their email to reset the password. So what we could do is find popular packages and target their developers, and then release a new version of that package that has maybe a backdoor built in. What's also very interesting about this bug is that it was 15 years old when it was discovered. So the bug was actually in the reset password function since this function was written the first time. So really long time where people could have abused it if they found it. But we didn't want to stop there. Taking over every developer's account creates a lot of noise, and people could get suspicious and block the attempt or clean up after the attacker if they notice it. So is it possible to gain code execution on the server and replace all the packages in a more stealthy way? This is what we wanted to find out. So we went ahead and looked what we could do now. Now that we have new attack surface, because now we have an account and can use more features than before, we can see that packages that are submitted, new ones or updates, are added to a work queue where then asynchronous workers will process them and eventually publish them. And this processing works like this. At first, the package is extracted and validated, and afterward, the documentation is generated using the PHP documenter tool. And finally, the documentation and the package download are copied to the package page where you can now see the package's README, documentation, and can download the package. And this also sounds really interesting. The extraction process and the documentation generation process sounds quite complex. A lot of file system handling, and also this tool, a lot of complexity where things can go wrong. So we looked into the code to see how all of this worked. At first, here's the code that extracts the file. So when you upload a package, you have to do it in the tar archive file format. And then this file is extracted with the archive tar package into a temporary directory. Then we had a look at the version that's being used of this archive tar package, and we noticed that the version was slightly out of date. They used version 1.4.7, and at that point, we looked up to see if there's a known vulnerability in there. And in fact, there was. There was CVE 2020-36193, and we looked at the description to see what exactly this vulnerability was about. The description describes that it allows write operations with directory traversal due to inadequate checking of symbolic links. And it gets more and more interesting with this because for once we now know that directory traversal has to be used and it has to do with symbolic links, but also writing files somewhere is very, very powerful in the PHP ecosystem, because once you can write a PHP file to the web root of a server with controlled content, you can basically just browse there and the server will happily execute your code for you. And then you can do about everything that the server could do. So to find out exactly how this vulnerability has to be abused, we checked the patch of the vulnerability. This is a very commonly known technique to just look for the patch and then see what was changed. And then you know exactly what they now prevent, what was previously possible. So in this case, the patch added these few lines that add another check. So whenever a file is extracted and it contains an element that is a symbolic link, type 2 in terms of the tar format, then it will see if the symbolic link points inside of the extraction directory or outside of it. And if it points outside of it, then it will be blocked and an error will be displayed instead, because this is now forbidden. With this, we knew that we somehow had to use a symbolic link that points somewhere else, but symbolic links in themselves are not really dangerous. It's only a pointer to somewhere else. We still have to write there. And to do that, we crafted our own tar archive file. And it looks like this. The first element in the archive is a symbolic link called symlink. It points to the web root and then to the file evil.php in this web root. The next item in the tar archive file is a regular file. As you can see, it has 49 bytes of content, so there's some content in it, but it is also called symlink. And then lastly, we have package.xml, which is a file that's needed by pair to do some more validations on the package. And if such a tar file is now extracted with the archive tar package, the following happens. What you can see here is a rough approximation of the file system of the pair server. At the top, you have the web root called public HTML. It contains, for example, an index.php file and other files that are reachable via the web. Below that, you have a temporary directory. One of them is used for the actual uploads, so the tar files. And the bottom one is used to extract the tar files there. In this case, our package is called myPackage, and it gets extracted. So at first, the first element is extracted. This is the symbolic link called symlink. It points to evil.php in the web root, but the file evil.php does not exist yet. It's only the link that exists. Next, the second item is extracted, and this is the regular file that is also called symlink. This causes the system to write to the file called symlink, but because it is a symbolic link, or was before, it writes to where the symbolic link points and not directly at the location where it is. So this causes the file evil.php in the web root to be created, and the content is arbitrary. The attacker can completely choose it. In this case, it's a simple PHP script that executes a command as a system command that is given via a get parameter. And then finally, the package.xml file is also extracted, but for the exploit, this is not really important anymore. So let's put the pieces together. We chained both of the bugs to first take over an administrator's account with the reset password functionality. Then we used these new privileges to create a new package and automatically approve it so that it would get added to the work queue and extracted. And during this extraction, the known CVE exploit in archive.tar leads to the file write, and finally our own PHP script lands in the web root, and we can just execute it. And with that, we can compromise all the pair packages with very little noise. And yeah, basically that's it of the journey on the backend side, because there's no much more room for lateral movement. On the server that hosts pair, there's only other stuff related to pair that's being hosted. So we could, for example, compromise the pair installers. But the real interesting thing for a real attacker would now be to backdoor all the packages and then wait until people install them and move into their network and install malware there. So to show it all, we now have a small demonstration about how to get a shell on the pair server.
All right, this is the third and last demonstration for today. So we have the same setup. We have a test instance of pair on the left, which is hosted on a VM with IP addresses. On the screen below, this is just test one, again, not real production instance. And to make our life easier for the demonstration, we're going to start a cron job every 5 seconds. On the real instance, it would, I think, take up to a day, but we don't want to wait for a day for the demonstration, so it's going to be quicker that way. So we know there is the admin account, but we don't know its password. So we can use the exploit to first fetch date of the server and try to brute force the only few reset tokens that may exist at that time. So we do a password reset request, and then we use this date to try to guess the token and change the password. And now we see it succeeded, and we can log in as admin and foobar. And this is super user. This is really cool. We can already start releasing backdoor releases for everybody. But we'll show you the second exploit that we found. So we create the malicious archive with two symlinks. First symlink as a link, then symlink as a file, and then finally the package.xml. We upload it, and when it's done, we see that the cron will trigger, and it will write the evil.php file under the web root. And if we access this file with the right parameter, we can execute arbitrary commands like id or uname.
Okay, now let's have a quick look at the timeline of this disclosure. We reported this in summer last year to the pair maintainers, and a few days after, they pushed commits to their GitHub that fixed this issue. But then it unfortunately took some months until these fixes were actually deployed to the pair instance. And in this time frame, people could have seen that there is a fix for a vulnerability and what it is, and try out if it has been fixed on the server yet. Unfortunately, to our knowledge, this did not happen, but it's always best if the fix and also the deployment of the fix are being done as fast as possible after another. If you can, you could consider moving to Composer, because packages are also present on Composer when they are at pair, at least for the very popular ones. And Composer and packages have far more active community support, and as we've seen, they are able to patch faster. Now let's have a step back and think about how we could prevent these attacks in general. First of all, we have to admit that our ecosystems are not robust against these attacks. And this is not only a PHP problem. It's basically in most ecosystems that these central components are built by volunteers and also maintained and operated by volunteers. So there can be bugs in there, and you can't really blame anybody if they do it in their free time, right? So in order to fix this, we want to focus on two actionable ideas that could help prevent these attacks. First, we could do impact reduction, reduce the impact, by doing mandatory code signing of software artifacts. And secondly, we can reduce the risk by applying all the security best practices. For the first part, the impact reduction, we want to have code signing. Because in fact, package managers don't have to be trusted. In the end, they are just simple tubes, a tunnel that you reach through to get what you want. And you don't want to have to trust this. You only want to trust the thing that you are getting. So if the thing you're getting, the artifact that you download, is signed by the developer that wrote it, then you only have to trust this developer's identity. And you get the identity via OIDC providers or via GPG keys, something like this, so that you can check the cryptographic signature of the thing you download. And if the signature is correct, then you know that it comes really from this developer. And then you only have to trust the developer and not the developer and the package manager. So this would already avoid many attacks on the package manager platforms. The worst thing that could happen now is you can't get a package because it's backdoored, but since you know that it's backdoored because the signature doesn't match, you can just discard it and not use it. But all of this only works if it's mandatory. Otherwise, there will always be holes in the system. For example, if package A is signed, then you would notice if it's being manipulated. But if package A depends on package B, and this package B is not signed, then you can't really use package A because you would have to download both of them in order to use the whole thing. But since you can control or check if package B is really the thing that the developer wrote, the whole code signing thing doesn't work anymore. So it has to be mandatory. One project that wants to tackle this is Zigstore. Zigstore is basically a public append-only ledger where signatures of all the artifacts of all the packages are being published at. And to sign the packages, only ephemeral keys are used for exactly the signing and storage. And it's kind of similar to TLS certificate transparency, where there are already these kinds of append-only public ledgers where certificate authorities are publishing all of the all of the certificates that they are issuing. So you could watch there and see if some CA is issuing a certificate for your domain that they're not supposed to do, and then you can intervene. And Zigstore also has protection against downgrade attacks, which is also very good for the security of the whole system. And suddenly, if you use Zigstore and if Zigstore would be integrated into your ecosystem of choice, you only have to trust the identity providers and not the ecosystem itself. And since the identity providers are usually big companies such as GitHub or Google, you know that they have much more money and people to make sure that their systems are safe and not breached, and really only provide those identities to the people that they should. The second part is code security, applying code best practices. So most backend services of these package managers are open source. There are some exemptions to this rule. For example, NPM. There's only the client that's open source, but not the backend. And you might think, as with all open source software, open source is nice, and that is true. But you also might think, it's open source, so surely some people have already looked at the code and made sure it's safe. But did really somebody do that? You don't really know. So who's auditing all this open source software? We do it, but we can't audit all of it. And code reviews take time, and they require money if you want to hire somebody to do it, and also paperwork and all this organizational stuff. So can some random open source project really come to a company and say, please audit our code? Also, there's bug bounty programs such as Internet Bug Bounty, and this particular one is supposed to pay out bug bounties to researchers that find vulnerabilities in popular software that's used all over the internet. But, for example, they didn't accept these bugs we presented today. So who would do it if not them? So there's maybe not that good of an incentive for other researchers to do it. And speaking of other researchers, we only know of less than 10 people in general that publish bugs in these targets in other package managers. So that's really a small group of people who, even if they wanted to, would have a hard time covering all of the code that is part of these ecosystems. And finally, we as outsiders, we don't have access to the infrastructure. We can only look at the code, in the form that it's published, for example, on GitHub, set it up ourselves and see if there's a vulnerability in there. But we don't really know how the production system is set up and can't see if there's a misconfiguration or other issues that can only be found if you look at the actual system. Also, the security of clients is important. Today we spoke about the backend services, but there's also the client part. And one problem is that they don't have a clear threat model. Usually a developer uses the client, for example, the Composer command line util to download a package. But what assumptions can you make? Like, should the folder in which the command is run, does it have to be fully trusted and safe, or can it be in any directory? Can you trust project files or other integrations that are present in this environment? Nobody really set the threat model for this. We did some previous work on this topic. For example, Git integrations in IDEs or in your favorite shell, and also other package managers. And the answers were really different. Some projects said, we don't see this as a security vulnerability. If a user runs a command inside a untrusted directory, it's their fault. They have to make sure to only run this on trusted files. And others took our report and fixed the vulnerability, either because they said, this is our threat model, or because they said, it's maybe not, but let's be sure and still fix it. But the gist is that it's not really defined and people don't really agree on what the threat model should be for clients. And in general, clients are more likely to receive contributions than servers. Clients are what the people use day to day, so they might want to have more features in there to make their life easier. And running a repository server, way less people do that. So let's conclude today's talk and come back first to the question that we asked in the beginning. Could we compromise a good chunk of the internet? Yes, we could. And it's really scary because the attacker level, we are seasoned security experts, but there are a lot like us out there, and even some that are not acting in good faith. So there are really some people who could have found this from a skill point of view and could have abused it. Looking at the time that it took to find the bugs, it was less than a week. So again, if somebody with the same skill level wants to find these bugs, they can. They just have to sit somewhere, look at code for some days, and probably would have found it. And when we look at the money, it was not even relevant in this case. We didn't need big servers to do this attack or something like this. Just download the code and read it, really. This leads us to the usual suspects of open source software security. I already said there's this thing where people think, it's open source. Surely somebody has looked at it, but did somebody really do it? And there's always lack of maintainers and lack of security reviews. If you want a feature in an open source project, you can ask for it, but the maintainer doesn't owe you something. You don't pay them to include it, so it might not get added. And the same is true for security fixes and stuff like this. Most maintainers want to fix them, but maybe sometimes they don't have the time, they don't have the right know-how. It's a difficult situation. So yeah, DevSecOps teams really have to apply all the supply chain best practices that they can, so they can make sure their environment is as strong as possible, so that some vulnerability occur in some of the other parts, they don't have that much impact. But on the good side, we see initiatives like Sigstore that really look promising and are already being integrated into some ecosystems. And if this trend continues, at some point we won't have to trust the middlemen, the package managers anymore, and the whole ecosystem will be one step safer. And of course, if you can, audit your package managers. If you have a security background, if you know a little bit about code and security, why not look into your package manager, that you use all the time? Try to see if there's a vulnerability in there, and if you find something, please report it responsibly so that it can be fixed, and everybody will be happier afterwards. Now we have to give big kudos to all the maintainers that helped us with these vulnerabilities. So for packages, that's Niels, Jordi, and Stefan, who are really fast to fix and really pleasant to work with. For pair, it's Chuck, Ken, and Mark, who also helped us get this vulnerability fixed and then finally deployed. I assume working on such a legacy code base is not that easy. So thanks to them. And if you want to support them, then you can do it via these links, via GitHub or Open Collective. And if you are using any of their projects, especially in a commercial sense, then I would really appreciate if you would fund them. All parties would benefit from it, because the software that you are using can get better and more secure if there's more funding to maintain them and maybe do an audit on them. If you need more or want more technical details, you can find them in our several blog posts on blog.sonasource.com, or you can talk to us, message us. We will be happy to answer questions. And if you loved what you saw today, you can also join us in the journey of making the open source world more secure. We work on a lot of interesting targets. That's it from us. Thanks for listening to our talk. We hope you enjoyed it.